Welcome to lesson 4.2, all about inverse derivatives. And this is the last family of functions that we're going to talk about. If you go into BC calculus or you go into any higher level math classes in college or do any further research on your own, you'll learn about rules for differentiating other types of functions, but this is the last main one that we are going to see through the Calc AB course. And the nice part about this section is that it will help us to generalize section 4.1, where we talked about derivatives of exponentials and logarithms, which are inverses of each other. We're going to generalize how we differentiate any functions that could be called inverses of each other. So the big thing is, let's define or redefine inverse, and we'll go in pretty simple terms of it. If you're given a function f of x defined by the set of points x comma f of x, or xy, f inverse of x with that -1 inside the function notation denotes the inverse of f of x and is defined by the set of points f of x comma x, given that f of x is defined for those x values. And ways that you might have been told or learned to think about inverses in the past was that an inverse swaps the domain, the x, and range, y, for f of x. Inverses also cancel each other. Like in the case of e to the natural log of x, the e and the natural log would cancel, and that would just be x, because those are inverses of each other. The other thing we want to look back at is how we actually develop the inverse of a function. Because certain ones are natural, e and natural log, addition, subtraction, multiplication, division. But even something like this, where f of x equals 5 times the quantity x minus 2 cubed minus 1, we can develop a function that would cancel that out. That would be defined as the set of points f of x comma x for this function. And so if you recall, let's rewrite this as y equals. And if you recall, the idea of swapping the domain and range like we talked about here, if you want to build the inverse of a function, that is all you do, is you swap the x's and y's. And if I want to write the inverse as a function of x, all I have to do is solve for y. So we'll do a couple steps at one time. We got x plus 1 all over 5 equals y minus 2 quantity cubed, and finishing up solving, we will get the cube root of x plus 1 over 5 and add this extra 2 on. And we could change that to read f inverse of x equals this cube root of x plus 1 over 5 plus 2. Big thing is, don't get confused. X to the -1 is still corrected by doing the reciprocal. The reciprocal of a negative exponent changes that exponent to be a positive. That was something we've seen with power rule and something we've worked with a lot this year. On the other hand, putting that -1 inside your function notation denotes the inverse of f of x. This is not the reciprocal of f of x. So moving along, recall that our goal for this lesson was to talk about inverse derivatives. And so when looking at the derivative of an inverse function, the derivative with respect to x of f inverse of x, we're going to use a similar algebraic manipulation that we used for working with e to the x and natural log of x, and that is to start with a derivative that we know. The derivative with respect to x of x is equal to 1. I'm going to go ahead and rewrite that as f of f inverse of x. Those are inverse operations, so they will cancel each other out. That is equivalent to x, which means its derivative should still be equivalent to 1. And notice, since it's f of f inverse of x, the derivative would involve using chain rule. And so derivative of our outside function f would be f prime of the inside function left alone, f inverse of x, times the derivative of f inverse of x, which is the one thing that we don't know yet. But that would still be equal to 1. And now solving for the derivative of the inverse function of x, all we'd have to do is divide both sides by f prime of f inverse. And that will give us 1 over f prime of f inverse of x. And that will always define the derivative of the inverse of any function f of x. And visually, in thinking about how the inverse relates to the original function, if we were to graph this situation, let's say we had something that looks like this. This would be something like our e to the x function maybe. Well, we get the inverse by reflecting over the line y equals x. And we already know what the inverse of e to the x is. It would be natural log of x. And all this rule for differentiating inverses tells us is if I know the derivative at some point x comma y, and I know the slope of the tangent line, in this case f prime of x. Well, when I flip this function over line y equals x, our inverse coordinate would be y comma x. And what our rule tells us is when I look at the derivative at this point, it will be 1 over that f prime value that we looked at previously. The derivative at a point on the inverse is the reciprocal of the corresponding point on the original function. And so let's zoom back out and take a look at the first two problems we see right below this box. So if f of x equals cosine of x minus 6x, and I'm even going to define my inverse function at negative 9 pi to equal 3 pi over 2. I want to find the derivative of the inverse of my function at x equals negative 9 pi. So what I'm looking at is the derivative with respect to x, and I'm going to write down a little subnotation to say at x equals negative 9 pi for the inverse function. Well, how we're going to define that is 1 over f prime of f inverse of negative 9 pi. And notice we already have part of that. We already have f inverse of negative 9 pi back here. It's going to be 3 pi over 2. What I'm missing is my f prime function. Well, given my original f of x, I will notice that f prime of x would be negative sine of x minus 6. And so what we want is f prime of 3 pi over 2, which would be negative sine of 3 pi over 2 minus 6. Sine of 3 pi over 2 is a negative 1. So negative 1 is going to be a positive, and 1 minus 6 will give me a negative 5. So 1 over f prime of 3 pi over 2 will be negative 1/5. Just notice the link between these two values. My derivative at the point 3 pi over 2, negative 9 pi is negative 5. And for the inverse derivative at my inverse point, which is negative 9 pi, comma 3 pi over 2, that is just going to be the reciprocal. And now looking at example 2, if f of x equals x squared, and one thing I want you to add for x greater than or equal to 0, because if I deal with x squared, which is this parabola, and I try to make its inverse function, well, that wouldn't pass the vertical line test, and so it wouldn't be a function. But if I eliminate half of its domain, I'm going to eliminate this half of my inverse, and now it will be a function. So anyway, getting back on track with the problem, f of x is x squared. For x greater than or equal to 0, find the derivative of f inverse of x at x equals 4. And so we want derivative with respect to x of f inverse of x, and we'll go with a little subnotation saying at x equals 4. And that's going to be 1 over f prime of f inverse of 4. So the only difference between this and the first problem is we also have to start off not knowing what f inverse of 4 is. That's some number and we don't have it right now. But setting it up in this way, if I take f of both sides, notice how I'll get 4 equal to f of n. And I have a rule for the function f. This will be 4 equal to n squared, because f of x was defined as x squared. Taking the square root, I will get n equal to 2. And notice I'm not going to worry about plus minus because of the restrictions I have on the original problem. The restriction I have on the f of x function making x greater than or equal to 0 causes my inverse to always be positive, so I'm going to focus on a positive 2. So now I'm dealing with 1 over f prime of 2. I still need f prime of x. Well, starting with an x squared, f prime will be 2x, and f prime of 2 will be 2 times 2, or 4. And we will get 1 over 4. And all this is really serving to do is to give us a slightly better understanding of the relationship between any function and its inverse. Because a lot of the functions that we deal with, things like squares and square roots, cubes, cube roots, natural log of x and e to the x, this allows us to see some links between those functions at a slightly deeper level mathematically. And what we'll finish up with is taking our new knowledge of how to deal with derivatives on an inverse function and applying that to our trig functions. So, building up derivatives of our inverse trig functions. Please pay attention to this notation, straight from the AP exam. The inverse of a trigonometric function may be indicated using the inverse notation that we've been using, or with the prefix arc. And the reason why using something like arc to say arc sine is the inverse sine function, recall how if we saw something like sine squared of x, we thought of that as being sine of x quantity squared. Well, what we don't want to get confused with is thinking that this means sine of x to the negative 1. That is not the case. And so what we're going to want for developing these derivatives quickly is to recall our Pythagorean identities for trig functions. So sine squared plus cosine squared equals 1. Dividing that all by cosine will give us tangent squared plus 1 equals secant squared. And our last one is 1 plus cotangent squared equals cosecant squared. These are helpful in general, but also helpful for understanding how we're going to develop the formulas you see here. I'm going to say at this time, if you don't care too much about seeing the proofs for some of these and you would rather just move on to the rules and getting around to memorizing your formulas, I'm going to have a little cutscene come up and tell you exactly where to fast forward to so you can move right along. But if you would like to see the proofs, please stick around. So our first one, dealing with the derivative of sine inverse of x. So sine inverse of x, and recall we're still working with 1 over f prime of f inverse of x. When I deal with sine inverse of x, note that your original function will be sine of x, and f prime would be cosine of x. So what we end up with is 1 over f prime cosine of f inverse of x. And our inverse function is sine inverse of x. Now that is technically the derivative of the inverse function, but there's a way that we can clean this up quite nicely, and that is using the Pythagorean identities that we have up top. Cosine would be defined as square root of 1 minus sine squared of that inside function. And sine squared of sine inverse of x will just leave us with 1 over square root of 1 minus x squared. The sine and the sine inverse here cancel out, and all we're left with is an x and a power of 2. Well, recall for yourself that when we deal with derivative of sine of x, we get cosine of x, and when we deal with the derivative of cosine of x, we get negative sine of x. The biggest change that comes about when we take these derivatives is that negative sign when we go from cosine to sine. The same exact thing is going to happen when we switch from sine inverse to differentiating cosine inverse. You're going to get the same exact form of your derivative, but bring in the negative sign. So if you can remember one of these, you can remember both. They only differ by a negative sign. Looking at tangent inverse of x, your original function would be tangent of x, and derivative of tangent is secant squared. So setting up using your formula for the inverse derivative, we have 1 over f prime, which is secant squared, of the inverse function that we have, in this case tangent inverse. Again, we're going to use another one of those Pythagorean identities. Well, secant squared is tangent squared of x plus 1. So we're going to get 1 over tangent squared of that inside function tangent inverse plus 1. And notice again, tangent and the tangent inverse will cancel out. All you're going to be left with is that x in the square, and we'll get 1 over x squared plus 1. And these things continue to work in pairs. Tangent and cotangent are very closely related. Just like with sine and cosine, they're only going to differ by a negative. And so derivative of cotangent inverse of x is still going to be 1 over x squared plus 1, but with a negative in front. And so these four are the most common inverse trig functions that we run into. So make sure at this point we work on memorizing them, and really think you only need to memorize sine inverse and tangent inverse because cosine and cotangent come directly from those two. And the last two, put a star by them. They also only differ by a negative sign, but they're a little bit weirder. The derivative of the secant inverse is 1 over absolute value of x times the square root of x squared minus 1, and cosecant is just the opposite of that. But those two rarely pop up in any sort of application or anything that would be vital to us. So just keep them in the back of your mind in case you need to use them during the practice. But the big thing is the four that I've highlighted at the top. And so let's try to finish up by using these. One last note to make before we do that. Just like with trig functions, the inverse trig functions are all chain rule problems. And so derivative of sine inverse of 3x, we have an outside that is sine inverse of the inside, and an inside that is 3x. So we're going to get 1 over square root of 1 minus, in this case that x from the rule that we learned up top goes with your inside function. So we get a 3x quantity squared times the derivative of 3x, which is 3, and we'll have 3 over square root of 1 minus 9x squared. In the second problem down here, we have tangent inverse of 2x squared. So outside, we'll differentiate using the rule for tangent inverse with an inside function of 2x squared. So for tangent, it's 1 over our inside function squared plus 1 times derivative of the inside function, which would be a 4x. And putting that all together, we have 4x over 4x to the 4th power plus 1. And finally, cosine inverse of 5x to the 6th. So we'll have an outside following our cosine inverse rule, and an inside of 5x to the 6th. And so we'll get negative, remember this is the same as our sine inverse, just with a negative sign, square root of 1 minus our inside function squared times derivative of that inside function, which is 30x to the 5th, and putting that together, 30x to the 5th, make that overall negative, square root of 1 minus, that would be 25x to the 12th power. And so this lesson involved a lot of pure mathematical thinking, more conceptual mathematics, not so much with application of the concepts to real-world scenarios. Again, just something that can give us a better understanding of the relationship between any function and its inverse using the calculus concepts that we've been using over the past couple units. So please make sure, review and summarize your notes. Again, get down the main formulas that are coming out of this, which are your inverse trig derivatives that I've highlighted. Also go back and highlight your rule for the derivative of any inverse. And when you're ready, move on to the practice for 4.2. Thank you.